Good morning. I'm Liz Goldsmith from the TIA's Fiber Optics Technology Consortium, and I'd like to welcome you to this morning's webinar, Where Do We Go From Here? A Fork in the Road for Multimode Fiber. Presenting today will be Robert Reid from Panduit. Before we start, I'd like to cover a few housekeeping items. Our web conference is scheduled to run for an hour with 15 minutes of questions at the end. Robert plans to answer questions after the webinar finishes, but feel free to submit your questions at any time using the Questions tab on your screen. Audio is available only through your computer. Occasionally people have trouble with the audio coming through clearly. If that happens to you, please try logging out of BrightTalk and then logging back in, as that usually fixes the problem. It has always been fine on the recorded version, so you can listen to the program on demand if you end up with a problem today. I will be sending out a link to the on-demand version of the webinar later today. Attendees will receive 1 BICSI continuing education credit for participating in this conference. The email to request CECs will be on the last slide. It takes several days to process them, so please be patient. CECs are also available to people who watch the webinar on demand. Now, let me tell you briefly about the TIA's Fiber Optics Technology Consortium. The FOTC focuses specifically on structured cabling. The section was formed 23 years ago as the Fiber Optics Land section, and our mission is to provide vendor-neutral information about communication solutions using fiber optic technology. Our members have traditionally been a mix of fiber manufacturers, cablers, and manufacturers of test equipment and electronics. On our website, www.tiafotc.org, you will find fiber FAQs, standards information, articles, past webinars, presentations, white papers, and industry research that we've conducted. We also have a free network architecture model that you can download to compare the suitability of different standards-approved architectures for your installation. We know that earning continuing education credits is a top priority for many of you. We are pleased to offer you a library of webinars that are available on demand on our BrightTalk channel. We have one webinar coming up in January, and we have many that were presented in 2017, which are still eligible to earn CECs. Just a heads up, not all the webinars on BrightTalk are eligible, and not even all the webinars on the TIA channel are eligible. If you don't hear me introducing the webinar and talking about CECs, you probably can't earn one. Now I'd like to ask you for a favor. As part of our effort to deliver the type of content that you value, we will ask you a few polling questions during the webinar. Please take the small amount of time necessary to answer these questions. It is valuable feedback for the presenting companies and ensures that we can continue offering our webinar series. And just before we start, please read this disclaimer from TIA. Because the FOTC is part of the Telecommunications Industry Association, we want to assure you that our webinars promote standards-compliant and vendor-neutral information. Now, let me introduce our speaker. Robert Reid is a Senior Technology Manager for Panduit's Data Center Connectivity Group in Tinley Park, Illinois. He currently defines product development direction for Panduit Data Center Connectivity Group and has been active in the fiber optics and photonics industry for over 30 years in the development of passive optical components, optoelectronic, and specialty optic systems. Robert has presented at many industry symposia, BICSI, Data Center Dynamics, Optical Fiber Conference, OE Fibers, IMAPS, and more. He has also participated in the development of the standard TIA fiber optic test procedures and has served as membership chair to the TIA FOTC. He is a member of ANSY's T11 fiber channel. Robert, I will now turn this over to you.
Thanks, Liz. Great intro. 30 years in the fiber industry. Actually, I have to update that because next year it's going to be 35. Wow, time flies. I wanted to talk today about primarily the evolution of multimode fiber and the kind of a paradigm shift that's going to happen in the next couple of years as we climb up the data rate curve. What really is important is, and what drives fiber requirements is really transceivers. So most of the talk is really about transceivers driving fiber requirements. Wanted to talk about the plethora of transceiver form factors that are out there. I think we've got a polling question related to what you guys are seeing in terms of what you have to support in terms of transceivers. Briefly talk about transceiver controlling standards outside of the application standards set forth by IEEE and ANSI and so forth. Really more about the manufacturer supply agreements. Talk about a roadmap of fibers. I've been in the fiber industry, like I say, for 35 years. When I started, we didn't even have OM grades. We had 5125 fiber and 100/140. We're seeing a paradigm shift in terms of needs for customers, and we're seeing a lot of customers swapping over to single mode fiber in particular. I wanted to talk a little bit about that in the context of cost also, because cost is important. We have limitations as the TIA FOTC. We have to talk in terms of relative cost. We really can't. We have to be agnostic in that respect. And you're going to finish up with what's beyond 100G, 128G for fiber channel. The talk is really light on fiber channel, even though I'm on the committee. It's really IEEE roadmap and transceivers related to Ethernet. The same roadmap, the same products that we talk about apply for both fiber channel and Ethernet. A lot of words here, but I wanted to lead you through kind of the evolution of multimode fiber. Again, I worked with the first commercial multimode fibers in 1982, making fiber couplers with them. 140 micron fiber, 5125 fiber. These are very low bandwidth fibers. The bandwidth of these fibers was measured differently than we do today. These were the first fibers that started to show up in telecom networks. In the 80s, we really saw further applications of multimode fiber, in particular. Some of the examples I've laid out there, PBX, line extenders, modems, and so forth. This is when we shifted away from 5125 fiber to 62.5 125 fiber. Most people think that 62.5 125 was the first multimode fiber. It was not. Actually, 5125 was, both in this country and in Europe. And the reason they went to 62.5 was it was easy to couple to LED-based transceivers, made for a more cost-effective transceiver. 90s, multimode fiber really starts to propagate into backbone applications, replacing UTP, where the reach of the solutions are greater than the reach of UTP. We see a lot of, I'll call them proprietary transceivers. I'll give you a picture here in a minute. FDDI, SCON, ATM, a lot of transmit-receive pairs for multimode fiber. So, and for the most part, these are not pluggable transceivers. These are board mount, soldered to the board transceivers. The paradigm shift came in the late 90s, mid-late 90s, at the front of VCSEL technology and the need for gigabit transmission. Really, superluminescent LEDs, SLEDs, kind of topped out at 622 meg, and that's where we saw the conversion to VCSELs and 1 gig. Late 90s, we started to measure bandwidth a little bit differently. We started to use differential mode delay. Prior to that, we were using a frequency-based measurement, basically with a laser, which wasn't indicative of the true performance of multimode fiber. And we started to look at grading the fiber with respect to its bandwidth. Here I've got the example of OM3, 2000 megahertz kilometer at 850 where the application is. We move into the 2000s, OM4, higher bandwidth fiber using the same grading characteristic, 4700 megahertz kilometer, really anticipating line rates above 10 gig and to support 25 gig line rates. So today here we are, OM3, OM4 fiber are pretty much the primary fibers for Ethernet and fiber channel applications. A lot of parallel multi-mode fiber solutions for both Ethernet and fiber channel using at least 4 pairs, 4 transmit, 4 receive. We also have BiDi solutions which are good for customers, basically serial duplex type LC-based transceivers. There is a hint that there's going to be a 100 gig BiDi solution here probably this month going into next year. Chromatic dispersion compensated OM4 and OM5 fiber for extending the 850 nanometer apps. Multiple vendors have solutions. And I'll talk a little bit about wideband multimode fiber OM5 for the SWDM emerging transceivers. That's really an enabler for beyond 100 gig, and that's where I'm going to finish the talk, at beyond 100 gig. So here we have, these are things I just pulled off of the internet, a bunch of early transceivers. Actually the one on the top left is actually a versatile link from Avago. It's an industrial transceiver for plastic optical fiber. And where we ended up really in the mid to late 90s prior to 1 gig is the 2 that are down in the bottom right hand corner. FDDI transceiver and a fiber or SCON transceiver, IBM SCON transceiver for fiber channel. So these were non-pluggable board mount transceivers, and really the fibers that supported these were low bandwidth 62.5 125 and low bandwidth 50 125 fibers. We're talking about bandwidth of less than 200 megahertz kilometer. So here we are today. We've got a plethora of solutions for 10 gig and beyond in a variety of form factors, pluggable and non-pluggable. Just an example here, the top right-hand one is a small form factor transceiver. This would support 10 gig, 1 gig or above, board mount in that case, and then SFPs and XFPs, pluggable transceivers, modularity. Anatomy of a simple transceiver. So this is a simple SFP transceiver, and it's a pretty simple device to where we've evolved from a lot of complexity on a transceiver to a very simple device. We've got basically an emitter and a detector, a laser driver and a preamplifier on the detector. Very simple, very cheap. In some cases there's an EEPROM on the SFP to do things like identify the vendor. Here's an evolution where we started at the dawn of 10 gig serial duplex transceivers. The first one there is a 300 pin board mount transceiver, very low risk design, very high cost design. And it's also low density because what happens with that transceiver is it gets soldered to the board and then the pigtails get plugged into the back of adapters on the front of the line card. So ultimate density of that is 4 of those devices per line card. Where we've gotten to with SFP Plus is 48 SFP Plus modular transceivers per line card. And you can see the evolution in size. You know, you're talking about 10 square inches versus 1.2 square inches. the power dissipation, 10 watts for a 300 pin, down to a watt for an SFP plus. And I think that's a high estimate. It's probably more like 0.5 or 0.7. I think the slide is a little bit dated. So I want to talk about the Ethernet roadmap. This is on the Ethernet Alliance organization website. It hasn't changed much in the last couple of years, but what I'm highlighting there is the 40 gig and the 100 gig Ethernet PMD for multimode fiber, physical media dependent, the transceiver. Basically what I have there is an MPO connector on the front. It can be a 12 fiber MPO connector. It can be an 8 fiber MPO connector. You have 4 transmit, 4 receive. Now for both the 100 gig with a 25 gig line rate and the 40 gig with a 10 gig line rate. So what I've highlighted here is kind of the evolution of the media device interface. So that's the connector on the front of the transceiver. So in IEEE terms, Ethernet terms, we've gone from duplex LC, starting with 10 gig, going to 40 and 100. The first 100 gig transceiver standard was the SR10, which for all intents and purposes is pretty much obsolete except for some specialty applications. And as I mentioned, the 100G base SR4 is out there, and it is a 4 transmit, 4 receive, just like the 40 gig SR4, 4 transmit, 4 receive. And the data center reaches across all of these, you're talking about 300, 400 over OM fiber, OM3 and OM4 fiber, down to where we are today with a 25 gig line rate, 70 and 100 meters over OM3 and OM4 fiber. So here's the roadmap for the transceivers going from high cost to low cost, and basically the same thing is happening above 10 gig. Is you're starting to take the components, the sophistication off of the transceiver, moving from left to right CFP all the way down to where we are today with QSFP 28, which is probably the most utilized higher speed transceiver form factor. So you're going from high cost, low volume designs to low cost, high volume designs. Now when that first 100 gig transceiver came out a number of years ago, I think it was 6 or 7 years ago, in the CFP footprint, a single device, a single mode 100 gig transceiver was almost $100,000. Now we're in the range of a few $1,000s. The standards that control these form factors are independent of IEEE and ANSI. These are manufacturer-run standards. They call them multi-source agreements between manufacturers. And these standards basically talk about the electrical pinouts, the geometry of the transceiver, insertion and extraction forces, things like labeling, and so forth. So we have a progression of these. This actually shows SFP, QSFP, and CFP. So here we are today, 40 gig, physical media dependent, the transceiver, SR4 over multimode fiber, 4 times 10 transmits, 100 and 125 meters of reach over OM3 and OM4 fiber. There are variants of this transceiver that give you 300 and 400. I think I've got a slide that talks to that. It's an enhanced version. It's not described in the standards at all, but using the same OM3 and OM4 fiber. And here's the variants for 100G, the PMDs for 100G. The SR10, the first one there that's highlighted, pretty much obsolete except for specialty applications. SR4 with a 25 gig line rate, and you can see the reach there, 100 meters. Both of these, all of these are 850 nanometer. Emergent technologies over the last couple of years, there's multiple vendors that have these bi-die. And what these do is set up bidirectional transmission over a single fiber using discrete wavelengths, 850, 900-ish wavelengths. So times 2, if I'd send 20 each way, times 2, I've got 40 gig. Now the coming standard is 100G. It's not a standard, it's a, we'll call it pseudo-proprietary transceiver to multiple vendors. The beauty of these systems are they use LC serial duplex channels that are legacy. So OM3, OM4, and now OM5 fibers. Oh, this is the extended reach version of the 40 gig QSFP that I mentioned just a second ago, showing OM3 and OM4 reach at 300 and 400 meters. That's where the original 10 gig SR standard was, so this harmonizes with that, and this is very common in the marketplace now, and fairly low cost. So we have a checkpoint question here, Liz. I'll bring it back to you.
Sure, thanks, Robert. As I mentioned earlier in my introduction, we're going to ask you 3 questions during the course of the presentation. It really helps us if you answer them. The voting apparatus is at the bottom of your screen. This question asks if you support any non-IEEE-based transceivers with your multimode fiber cable plant. Your options are bi-die transceivers, universal transceivers, embedded optics transceivers, extended reach versions of IEEE-based transceivers, or none of the above. Occasionally people have said to me, what if I have more than one answer? I would say choose the one that's most likely, and if it's really split, write it in as a question for me, and I can add the answers to the results. So I'm going to leave the voting open for a couple more minutes while Robert continues with his presentation. Thank you.
Thanks, Liz. And universal transceivers, that was actually in the polling question. So there's a lot of customers out there that are using legacy, low bandwidth, multimode cable plant, OM2, OM2 plus fibers, OM3, but they want to get the reach of a native 40 gig transceiver. So these have been put out there. It's basically a multi-wavelength solution, and it produces 150 meters over OM3 or OM4 and 500 meters over single mode fibers. So customers can support the legacy multi-mode cable plant, and a pretty reasonable reach of 500 meters covers most applications in the data center for single mode fiber. People like to have one part number. Coming is embedded onboard optics. So this is kind of like taking the modularity back to where we were when we started, is, you know, basically soldering the transceivers onto the board. These are board mounted transceivers. The example I give there is Arista's MXP optics. And there is an industry group called COBO, Onboard Optics, Consortium for Onboard Optics, that's working very actively and building capability to basically bring the transceiver functionality onto the card, which is kind of like copper, right? So I basically have a bunch of ports on a switch and ultimately drive the cost down of the total solution. Roadmap for multimode fiber, starting left to right, and the timeline's very loosey-goosey, and it's not linear. Just to give you a flavor of where we've come from, OM1 fibers, legacy, 180 megahertz, 200 megahertz kilometer fibers, OM2 fibers, 400 to 450 megahertz kilometer fibers, really at the start of the 1 gig Ethernet ecosystem. We have, and I don't know if everybody recognizes this, but we have an OM2 plus fiber that was popular for a while. It was, again, 10 gig fiber. I've colored it aqua. I think a lot of the solutions in the market for OM2 plus were aqua. It's not described in any standard. It's basically a 900 megahertz kilometer fiber that was a lower cost version of full OM3 fiber. And full OM3 fiber is a 2000 megahertz kilometer fiber, basically launched prior to the ratification of the 10 gig Ethernet standard in 2002. So we have an OM3 fiber looking forward to 25 gig. We have the launch of OM4 fiber, and now we have what we'll call dispersion compensating fibers. Multiple vendors have these now. They're basically OM4 fiber with a special characteristic that optimizes chromatic dispersion. I'm going to talk a little bit about OM5 fibers, wideband multimode fibers. There is a series of transceivers coming out, shortwave length division multiplexing using multiple colors, around 850 to 950. And expected will be OM5 plus fibers that not only have the capability of that band of wavelengths for wave division multiplexing, but will also have dispersion compensated corrected characteristics. So here's the standard. This was completed in 2016. Describes the characteristics of wideband multimode fiber as ultimately OM5 fiber. I think I might have missed a slide here. Let me just back up. Nope, I didn't. So what I have here is I wanted to talk about dispersion compensated fiber. As I mentioned, that there are a couple of vendors out there that are producing, like we had for OM2 fiber, we have an OM2 plus fiber. Now we have an OM4 plus fiber. So this extends the capability of OM4 fiber and basically adds more reach. And the way it works is the laser, the VCSEL is not spectrally pure, so it emits multiple wavelengths. Predominantly the off-axis portion of the beam gets coupled into the higher order modes of the fiber. And what happens is those higher order modes of a different wavelength get delayed. So I'm hoping you're seeing it here. The blue light is delayed with respect to the red light, and I'm just saying blue and red as two discrete wavelengths. And what happens is there's a spreading of the pulses that get sent over the fiber depending on the relative wavelength, lambda 1, lambda 2, what gets emitted from the VCSEL, and how it ends up in the modes of the fiber. So basically higher order modes are coupling the blue light, we'll call it the blue light, and going straight through is the red light. And what you get is an overlap of power of the blue and we'll call it the blue and the red. And what it does is it spreads out the pulse. This was not well understood in the measurement, the DMD measurement that we talked about earlier. And this is an additional characteristic that increases the bandwidth of multimode fiber. So we call those OM plus fibers, OM4 plus, OM5 plus. So normally what we do is, and I have the bandwidth in megahertz per kilometer plotted on the horizontal axis. And this is just a frequency distribution of occurrences of bandwidth from a fiber vendor. So normally what happens is anything that is greater than 2000 megahertz kilometer to 4700 megahertz kilometer, that gets sorted as OM3 fiber. All these fibers come from the same process. And anything above 4700 megahertz kilometer gets sorted as OM4 fiber. And then within that, there's a subset that has a dispersion compensating characteristic that gets sorted also. So these, I'll call these additional sorting metrics for OM4. So we have, as a result of this production, we have OM3, we have OM4, and then with these additional chromatic dispersion compensating sorting metrics, we have OM4+. And so you can basically do the same with OM5. You can have an OM5+. So I've got another checkpoint question here, Liz, and I'm going to send it over to you.
Yes. So this question, we're trying to ask you, what types of fiber are you specifying and or installing today? Mostly OM3. B would be mostly OM4. C, mostly single mode. D, a mix of OM grades depending on the application. And E, none of the above or not sure. Once again, I will leave the polling questions open for several minutes to give all of you a chance to respond, and we'll let Robert continue with the presentation.
Thank you, Liz. So in terms of grading these different fiber types here, the definition within the sectional specifications for the fiber talk to a gradation in the EMB, the bandwidth of the fiber at 850. And then we have an additional metric here that really only applies to these higher types of fiber, the OM4+ and OM5 specifically, out at 853 or 953, where I have to have at least in the specification, I have to have at least 2,000 megahertz kilometer. And at 850, we've got, OM4 fiber is 5,500, OM5 fiber is 4,700. So all of these fibers are designed to work at 850. The best of all of these fibers at 850, the single wavelength is the dispersion compensated fiber, OM4+. The fiber that produces the best SWDM performance obviously is OM5. And again, OM5+, which is not on this chart, will be a superior performer to OM5. It's not to say that SWDM applications are just relegated to OM5. Any of these fibers can be used for SWDM applications, albeit at a shorter reach. There we go. In terms of today's data center, we've got a mix of these fibers. So what we're seeing is 62.5. That's probably an overestimate of what's being deployed in data centers. OM2 is really disappearing. I think 62.5 will be around for a long time. Maybe not so much in the data center, but in military, government, industrial applications. It's going to be around for a long time. We're seeing the expansion of OM4. Now, when I say OM4, I mean OM4 and OM4+, because OM4+ is compliant to the OM4 standard. And when I say OM5, going forward, I'm going to mean OM4, OM5, and OM5+. So the green band, the purple band are really OM4 and OM4+, and OM5 and OM5+. So really what you're seeing here is OM4 becoming the majority application and OM3 kind of disappearing over time. We've got new challenges with fiber. We've got these flat architectures, that leaf spine architectures where everything is connected to everything else. In a hierarchical switch design, everything isn't connected to everything, and there's much more fiber, much more ribbon fiber in particular in these solutions. We're seeing a shift in where the servers are ending up. So that middle graph, sorry for the eye diagram, the middle graph there talks to where the servers are ending up. And this is the total number of servers, which is really, if you look at the opportunity for transceivers and fiber cable and fiber, this is really scaling with where the servers are ending up. So what you've got there in kind of an orange-brown is standard enterprise applications. And in green, you've got cloud service provider, I'll call them hyperscale applications. And what we're seeing today is 40% of the servers are in hyperscale. And that's growing. And some people are saying, 70%, 80% of all servers are going to be in hyperscale by 2019, 2020. What customers are also looking for is kind of a seamless integration of the cable plant. There's a lot of investment in cable plant. How do I take those multimode fibers and spin them up to higher data rates? So it's really a concern going from 10 to 40 and 100, and now 25 to 100 and beyond. And the scale and size of these data centers is getting pretty outrageous. I've got 3 examples here. I've got a Google data center that's kind of in the middle of the country. I've got SuperNap in Las Vegas. There's multiple buildings like this all sprinkled around Las Vegas. And several years ago, we would have thought, 250,000 square feet for a data center was a mega data center. The data center on the right-hand side there, the Langfang DC in China, is 6.3 million square feet. Don't see any end to it. So when we look at the reaches of the multimode solutions in particular, maybe multimode fibers, and I think these hyperscale guys are finding this out, are not appropriate for some of these reaches. Because you're talking about a building that's over 1 kilometer long on the left-hand side there. Not a multimode necessarily application. So just in terms of what I see for macro trends for transceivers, so you got to support the installed base. So the installed base is, and I put some fiber channel ones in there, 1632. We now have 128 fiber channel, 40, 100 on installed multimode fiber. So lane rates have gone up to 25. There's now technology that enables possibly 50 in terms of just straight modulation, no encoding. So this is going to affect the future of single and multi-lane optics. So you can envision, a 50 gig modulation, maybe PAM encoded up to 100 gig. So you can envision a duplex, serial duplex transceiver, LC based at 200 gig. Wideband multimode fiber, I think this is going to become pervasive. Technology is pretty mature. The idea there is to work backwards, not have more lanes, because that's problematic for customers when they want to recycle cable plant, but have, ultimately serial duplex is if you could communicate over serial duplex for the next several years, that would be great. And also, which is going to affect the multi-mode ecosystem, is the emergence of cost-effective single-mode optics. And really it's driven by the hyperscale guys. They want the single-mode optics for the reach. They want to do breakout. They want to take it down to the baseline rate. They want to do breakout. And these guys are driving the market and driving the cost down on these single mode optics. Give you a snapshot of the different port speeds that are shipping. And this doesn't include fiber channel. Fiber channel's got its own ecosystem, and there's multiple speeds there, all the way from 1, 2, 4, 8, 16, 32, 64, 128, and a roadmap to go out to 512. But 2008 we had 3 different speeds, and now we're dealing with 1, 10, 25, 40, we're going to look at 50, 100, 200, 400, where's it going to end? And this is interesting because this is the highest volume, higher speed transceiver, which is the QSFP 28, 100 gig, which is kind of the benchmark today. And we've got a Pareto of units shipped. And you can see today that SR4 over multimode fiber is the largest section of the pie. But it's not the fastest growing. The fastest growing is actually CWDM4, CL4. The second fastest growing is PSM4, parallel single mode. Both of those, the green and the blue, are driven by hyperscale. And the cost is being driven down by volume, the amount of transceivers that these guys are consuming. People like to do breakout. So this is another trend that we see. People don't use necessarily 100 gig transceiver at 100 gig native across the channel. They will do 25, 425s. Or if it's a 40 gig transceiver, they'll do 410s. So in this example here, I'm taking the uplinks on this switch. This could be a leaf switch. I'm taking the uplinks and then breaking them out into 4 LCs. So I've got 4, in this case, 4 10 gigs coming off of each uplink. So instead of 4 40s for uplinks, I've got 16 10s. Now the advantage of that is one of scale. So if I do that breakout on those uplinks, instead of only being able to support, let's say each one of these switches has 4 uplinks, instead of being able to only support 4 spine switches, I can now support 16. That's given that the switch ports in the spine are also similarly broken out. So in this case here, instead of having 4 spines and let's see, 32 leaves, I can have 16 spines and 128 leaf switches. So it's a scaling thing. So the ability to do breakout gives the ability to the architect to scale the fabric horizontally, so I can have more spine switches. So this is a macro trend that we're seeing in data center, more fiber, hyperscale data center in particular. Again, single mode is important, and single mode for hyperscale is very important, and they like to do breakouts. So along comes parallel single mode. You can basically run 40 gig native, or you can break it out. Each of the so this presents as an 8 fiber connector, 4 transmit single mode and 4 receive single mode. So this is in the standard. We've got a PLR4, and it supports 10 kilometers over single mode fiber. And we've got a light version of this, which is a 1 kilometer over single mode fiber. Well, that's the standard, but what the hyperscale guys got together and they said, we want to make it even cheaper. So there is an MSA, multi-source agreement, for 100G PSM4, which is basically similar to the last slide, and it's a very decosted version. I don't need 10 kilometers. I don't even need a kilometer inside of a data center. really only need 500 meters. So what they've done is they've de-spec'd the optics. This device actually has a single laser. So there's only a single source in this, but there's 4 lanes. And what they do is the laser runs at DC. It's just a lamp. And integrated in line, it's a power splitter. So I split out 4 ways, and then I have an inline modulator in each of those lanes integrated into the device. So these are very cheap, and like I say, 500 meters is, even for that data center example that I showed, the Langfang data center, this would cover a lot of ground. The downside of this is traditional single mode transceivers that support 10 kilometers, very highly spec'd, and might have 5-6 dB of budget. Well, when you start to de-spec these things, you've got, in this example here, you've got 3 dB now instead of 5 or 6 dB. So that allows you a certain length and a certain amount of connector loss in the channel. And the other one that we see, and this is the previous one's very popular at Microsoft. This one's very popular at Facebook, a CWDM4. So this is basically LC based. And the disadvantage of this compared to the other one is you can't obviously support breakout because it's LC based. So it's 100G over serial duplex, 4 colors inside of the transceiver, and it's also de-spec'd. So it's the cheapest one is what they call OCP, Open Compute version, is a 500 meter reach solution. And similarly, the cable plant is constrained, 3.5 dB of power budget there. So these are 2 very popular transceivers with the hyperscale guys. I wanted to talk a little bit about, and I can't talk too much about cost because we have to remain agnostic, but I thought this was a good comparison. This is actually from a couple of years ago, and it shows the cost of an LR 40G solution compared to an SR 40G solution. So when the standard launched, 2010, 2011, the relative cost of a single mode solution transceiver, LR4, compared to a SR4 transceiver, so we're comparing 4 wavelengths, LR4, versus 4 lanes of multimode, SR4. When it started, it was several times the cost. The single mode was several times the cost of the multimode. So now what we've settled down to, I think this is a little bit optimistic, but what we've settled down to is maybe 1.5 times. So if the unit of measure for the multimode transceiver is a 1 in terms of cost, the LR4, the single mode comparable version, is about 1.5. And again, to enjoy these types of ratios, you really have to buy a lot of transceivers. This is not one transceiver at distribution versus another transceiver at distribution. What I put together here is a cost scenario of a 4 cassette link for 100G LR4 versus SR4. Now, an LR4 channel is serial duplex, so it is LC based. The SR4 channel is 8 fibers minimum, could be 12 fibers. So what this model is made of is a 4 cassette scenario. So for the LR4, I have 4 cassettes, and those cassettes are 12 fiber cassettes. So the cost for the LR version is 1/6 of the cost because there are 6 channels per cassette. For the SR4, I've got MPO connectivity and MPO coupler panels all the way through. So I've got 4 MPO coupler panels. Now, if the link is near 0, I've got basically a very short link. I think I started at 1 meter or something like that. I've got a very short link, and I've got these components here. The components of the single mode solution are cheaper because I've got 1/6 of the cassettes associated with each channel. The multi-mode version is a little bit more expensive because I have MPO couplers and MPO connectors for each channel. So I started with probably a 2.9 multiplier just on the 100G LR4 to LR or SR4. So just the transceiver is about 2.9 times more expensive. But when you add in the components, it brings it down to about 2.1. You can see that in the red line there. And what happens is, as I add multi-mode fiber, and again, multi-mode fiber much more expensive than single mode fiber, the costs don't add up as much per unit length for single mode as they do for multi-mode. And there's a crossover point. And what we've calculated here is that, you know, beyond about 600, somewhere between 600 and 700 meters, there's an equivalency point. So if I buy the transceivers and the cable plant to support, anything beyond that is single mode wins in terms of total installed cost. If you took the 40 gig version where the multiplier is about 1.5, the previous slide, and you played the same game, you would see that the equivalency point of one solution for the other for 40 gig LR4 versus SR4 would be much shorter. So here's another checkpoint question. Liz?
Yes, thank you. This is the last checkpoint question. Obviously, it's about deploying MPO connectors. So are you deploying MPO connectors that attach to transceivers that are A, 8 MPO fiber connectors for SR4 type, which is 4 transmit and 4 receive, so the transceivers utilize all fibers, 12 MPO fiber connectors for SR4 type, which are 4 transmit and 4 receive, and they leave 4 dark fibers, 24 MPO fiber connectors for SR10 type, 10 transmit, 10 receive, and they leave 4 fibers dark, or 24 MPO fiber connectors for SR12 types. These are 12 transmit, 12 receive, and the transceivers utilize all the fibers, or E, none of the above, or don't know. So if you could just answer that final question, that would be much appreciated, and I will let Robert finish his presentation now.
Yeah, we'll note that D, there really is no SR12, but there are specialty transceivers in the market that use all 12 positions in the transceiver for transmit and 12 for receive. Okay, so beyond 400 or beyond 40 and 100 gig, we're going to start to talk about 200 and 400 gig, same roadmap that we showed before. There's candidate technologies to get there. Serial just means signaling, turning the VCSEL off and on really quick. Parallel is like a brute force technique. SR4, 4 transmit, SR10, 10 transmit, SR16, 16 transmit. WDM, multiple wavelengths as virtual lanes in the channel, and encoding. PAM4 seems to be the target here. So there are demonstrations out there. This was one that was done by Vertically Integrated Systems in Germany. Last year, they drove a specialized VCSEL driver and a specialized receiver and achieved 2.2 kilometers of multimode fiber, 54 gig, just by turning on and off the transceiver. So this kind of hints that, you know, maybe without encoding, we might be able to get to 50 gig. So you could envision, you know, if I was to do BiDi with this, let's say I could get a LC-based 50 gig each way. I could do a BiDi, 100 gig. Brute force, multiple lanes. You know, there was some movement to go to 32 fiber connectors and sophisticated keying and so forth. But I think there's more compelling tools in the toolbox to get there. This is not good for customers, these multi-fiber connectors. They're problematic in active data centers where I have to do changes with these at the panel. You can see the progression on the bottom there, 12 fiber, 24 fiber, 8 fiber. 12 fiber is historical. 8 fiber is optimized for SR4 with no dark fiber. And 24 fiber is a good connector to support multiple SR4s, particularly 8 fiber where I could have three 8s, let's say. SWDM transceivers, simply said, there's an optic, a passive optic in the transceiver that muxes multiple colors spanning 850 to 953 onto a single fiber, and then basically the same physical optic on the other end, much like the prism of the Dark Side of the Moon album in the picture there. Basically reversible, same type of physical optic that demuxes physically, optically onto 4 photodetectors. This is important going forward beyond 100 gig. So there are modules out there. Finisar and Lumentum are the two big supporters of this. 40 gig and 100 gig SWDM4 released. So SWDM4 4 wavelengths. It's a 100 gig toolbox, 100 gig and beyond toolbox item. Right now they're fairly expensive, but I expect that to come down. Power consumption's a little high. The one big negative here is that it doesn't support breakout. So I can't break these out onto the 25 gig lanes like I could a parallel optic transceiver. Just some grids. People are talking about possibly having a 2 wavelength solution for different speeds. So there's the grid for SWDM on the top, and this is proposed in IEEE as a 2 wavelength grid. Multi-level encoding, basically a way to, instead of having non-return to 0, 0, 1, I can break up that into 4 levels and generate 4 combinations of words. Instead of 0, 1, I've got 0, 0, 0, 0, 1, 1, 1, and 1, 0. These are symbols. So I can embed twice the information in a single clock cycle. Another tool. So if we think about a migration from serial duplex, what we can think about is 10 gig, 25 gig line rate to, with serial duplex, to 4 colors where I've got 100 gig in that last column. And then if I go from parallel, SR4, that's the 3rd row down, 1st column, I can migrate to 25 gig without changing the cable plant. And then ultimately the bottom right, if I use 4 colors in each one of those lanes, I can do 4x and facilitate a, if I had a 50 gig line rate, I could facilitate a 400 gig transmission. So here's one example. I could do 50 gig line rate. That would be encoded with PAM. So I have a 25 gig base rate encoded up to a 50 gig net line rate, and then having 4 colors with 4 positions gives me 400 gig. And this could be a potential transceiver. This might be one of the first ones that show up. CFP, I'm not going to talk too much about this, but this is a 8-lane version of the CFP MSA that we talked about at the start of the presentation. I don't think these are going to go too far. This one here is very interesting because it's a QSFP double density, and it supports 8 lanes in a variety of different ways. Each of the 8 lanes can operate at 50 gig, 4x the rate of QSFP 2028. One of the interesting things with this transceiver is there's a new connector, and we'll talk about that in a minute, associated with the 2-lane version of this. This is a very high density solution, so it's compared to the CFP8 above, the last slide, I can get 36 per line card. OSFP, which is another one, it's called the octal small form factor pluggable. It's a little bit less dense, it's 32. Both of these, the OSFP and the QSFP double density, have roadmaps with multimode fiber to produce up to 800 gig. This is the new connector I talked about, applicable to both the OSFP and the QSFP double density. This is just one of the configurations for the media device interface. It's a duplex connector. So on the top left-hand side there, that's kind of like a little bit bigger than an LC, but it has, you'll notice it has 2 ferrules in it. So I duplex those together, and I get 2 transmits on each side and 2 receive on each side. Just a relative comparison of the 3 form factors for 200, 400, and potentially 800 gig in terms of their power consumption, in terms of their relative size. These are all active MSAs supported by multiple module and equipment manufacturers. A couple more slides. I just want to talk about going forward with all of these tools that we have, multiple fiber pairs, multiple wavelengths, and encoding. And you can see the 2 existing standards at the top there, 25 gig SR and 100 gig SR4. What's new here is instead of SR4, just the straight lanes, we've got a .N. So I could think of SR4.N. So M would be the number of fiber pairs, N would be the number of wavelengths. So we've got a variety, with these tools, we've got a variety of configurations to use to get cost-effective optics. So the one that I had shown a couple slides back was the 400 gig SR4.4. So that's 4 fiber pairs and 4 wavelengths. Just a progression in terms of the standards. There's a call for interest on, basically what they're trying to do is reduce the number of lanes, because ultimately I think that's bad for customers. And we still want to have the ability to take and recycle the existing cable plant. We want to be able to support SWDM on OM3 and OM4 and so forth. I'm going to finish with a little bit of science fiction here. I like this one because I've been in the industry for almost 35 years next year. Early on in my career, I heard about a really interesting technology called angular division multiplexing. I'm talking about in the mid-'80s. So it looks like that this is starting to be commercialized. And what this is you can see the diagram there. The top diagram shows a single mode fiber with a single data stream going in, and I'm launching a single mode, I'm propagating a single mode through the fiber. Well, with multi-mode fibers, we have multiple modes. We have multiple fundamental modes. We've got, in fact, 19 mode groups. And each of these mode groups theoretically could act as separate channels. If I could excite these mode groups separately, I could have multiple channels. So I can theoretically have up to, if I used a 5125 fiber, I could have up to 19 channels in a single multi-mode fiber. It's not practical because of what they call mode coupling, but What some of the companies in the world have done is they've used this technology to extend the life of legacy multimode fiber. And they've gotten some incredible reaches at 40 gig over legacy 62, 125 fiber. It's expensive right now, but anything starting out is expensive. The example that I had at the start of the presentation of a $100,000 transceiver. So this is something I'm going to keep my eye on, and it may require, I note there, the development of a new breed of multimode fibers to optimize, to minimize the mode coupling between modes. This may require a 20 125 fiber. So a 20, it's not quite a single mode fiber, it's not quite a multimode fiber. You may have a fiber that supports 4 or 8 modes, and each one of these could be a separate channel. So this could be another tool in the toolbox with WDM, with PAM4, with raw modulation. I'm going to finish with, I'm going to call these few-moded fibers, I call them oligomode fibers, and I'm hoping that somebody trademarks that. Oliga is Greek for few. So these few-moded fibers, I expect to see these at some point in the future. As a summary, data center size continues to grow. Mega data centers, hyperscale, drive the need for especially single-mode fiber, extended reach solutions. They want breakout. So the multi-mode VCSEL solutions, it's seeing pressure from long wavelengths, decosted laser solutions. And now both of these support breakout. The PSM4 solution that I showed you supports breakout. The good side of multi-mode is not only does it enjoy the largest base right now, it's not the fastest growing, PSM4 is, with single mode, but it is the lowest energy consumption. VCSEL devices take a lot less energy than do laser devices. The big one that I underlined here, which may not seem like much, but dust and debris at connectors. If you've got active patch fields, I'm not talking about patch field in a central office where things don't get changed as much as they do in an active data center. The dust and debris immunity of the connector is huge, and having a reliable max for these higher speed applications is paramount. So operational issues kind of weigh in on the side of multimode solutions. People like migration. They like to take the legacy cable plant and, go through iterations of transceivers, supporting the legacy applications through breakout in particular. And in fact, most of the higher speed 40, 100 gig applications are not native. Most customers are using breakout. So these multimodes 4X solutions are going to perpetuate through 800 gig. I didn't talk about fiber channel, but they're going to perpetuate through fiber channel also, 512 gig and beyond. So 4 is a magic number. That's it. Liz.
All right. At this point, we're going to go to the Q&A portion of the webinar. We do have a few minutes left for Robert to answer some questions, and I'm going to give him a minute to review the questions that have come in. I will answer the 2 most common questions now. The first one is, how do I get my CEC? Please send me an email to that email address on your screen, liz@goldsmithpr.com. The second question I always get is, how do I get a copy of the presentation? If you look at the attachment section for this webinar, there is a PDF version of the slides that you can download directly. If you have any troubles downloading that, please send me an email, and I'm happy to send you a copy. Robert, we have probably 7 or 8 minutes for questions, so okay. Why don't I let you take over?
I'm gonna take a whack at some of these, Liz. I'll just restate the question here. I've got, what is the difference between SFP and SFP plus? Likewise, QSFP and QSFP plus. So SFPs, when they came out, supported 1 gig. SFP plus was the first SFP form factor to support 10 gig. So there's the difference. Same for QSFP. So we had QSFPs that were supporting less than 10 gig per lane. QSFP plus 10 gig per lane. Next question, can you use other than OM5 fibers when deploying SWDM optics? This is true. You can use OM4 fibers with reduced reach. You can use OM3 fibers with reduced reach with SWDM optics. I don't have those numbers handy, but I will say that the two form factors for the majority, the 40 gig and the 100 gig SWDM, for the majority of the applications in the data center are going to be covered with OM3 and OM4, believe it or not. So we've got 70, I believe, and 100 meters for the 100 gig SWDM, OM3 and OM4 versus 150 for OM5. And then I don't have the numbers at hand for sorry, that was 100 gig. For 40 gig, they're significantly longer beyond the reach of most applications. So OM3 and OM4 for SWDM are perfectly fine for 40 gig. What else do we got here? Is it possible to use multimode fiber taps with bi-die links? Seems like they steal a lot of power from the link. That's a true statement. 3 dB just in the split. Excess loss on the order of 0.4 of a dB plus connector loss. So you're talking about 4 dB-ish for the splitter itself. With bi-die, it's undocumented, but you get an extra 2 dB of margin. So you can't get the full reach of the channel, but there are a lot of scenarios where you can integrate fiber taps into bi-die links. And really, you're going to have to consult with your cabling supplier there. Let's see what I've got. Why is 62.5 so popular in industrial applications? Well, most industrial applications, the most popular transmission protocol is 100 base F. So 1300 nanometer over 62.5 or low bandwidth 5125 fiber that doesn't care about the modal bandwidth of the fiber. Let's see. Oh, there's a whimsical question in here. Noted the spelling of fiber versus fiber RE. Which is preferred and is there significance? Well, I'm Canadian, so I grew up spelling color with O-U-R and center with R-E, so that's force of habit. Fiber in this country is ER. RE, fiber channel, our marketing department always screws that one up because we've got, I put RE, fiber channel, ANSI fiber channel for storage networks, and they always correct it as ER. Let's see what else we've got here.
We basically have time for one more question now, but if your question doesn't get answered, I will have Robert send you an answer directly. So don't worry, every question will get answered.
Here's one right here. It says, as you consider multimode and single mode, do you consider the need to inspect and clean more important for single mode than multimode, more important for multimode than single mode, or equally important for both types? Well, just from a simple physics standpoint, I look at like, let's call it obscuration ratio of contamination. So I got a particle on the surface of a single mode fiber in the wrong place can affect the transmission much more than a 50 micron core. The same particle would not affect that as much. So obviously, single mode connectors, more important to inspect and clean. You got to follow inspection and cleaning practices implicitly. So before you mate a connector, inspect it. If it's not clean, clean it, and then you re-inspect it. Absolutely. So this is optics. Follow best practices. Liz, I think that was it. One more question?
Yep.
Was that it?
Yep. And any other questions that come in, I will forward directly to Robert, and he can answer and send you your answers directly. But at this point, I'd like to thank Robert for the great information and for all of the attendees of our web conference today for participating. Repeating that we will be issuing the Big CCEC certificates to attendees of the live web conference over the next couple of days, and also to those who watch the webinar on demand. I will be sending out a link to the on-demand webinar later today, so please forward it to anyone you know that might be interested in attending. To get your CEC, please send me an email at liz@goldsmithpr.com. And if you watch an earlier webinar on demand, please make sure that you include the name of the webinar in your email and the date that you watched it. I can look those things up, but it will take longer to get you your CEC. A copy of this presentation is available from the attachment section of this webinar. If you have any questions, just send me an email and I will send it to you directly. I encourage you to visit our Bright Talk channel to check for future webinars and to download tools such as our free cost model. Again, thank you very much for attending, and we hope you have a great day and a wonderful holiday season. Thank you. Bye-bye.